Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at rules of inference. So I'm not going to list all of the rules of inference here. There are quite a few. They are in the notes. So what we're going to do here is looking at inferring things, making inferences from premises. So we might get an argument that looks like this. These two statements that we're given, our starting points, they're called the premise. So what can we deduce from these two here? Well, if we use our valid rules of inference, from A and B, we can conclude B. If both A and B are true, then B must be true. So this is the rule of inference known as simplification. I'll just shorten it to simp. So if B is true and B implies C, we can conclude that C is true. So that is an example of modus ponens, which is another of the rules of inference. B implies C and B is true, therefore C is true. So let's turn our attention to an example involving quantifiers. Here we have three premises. The first says, for all x, cat implies mammal. In other words, every cat is a mammal. The second premise basically says, every mammal is warm-blooded. I've just shortened it to warm. The third premise tells us that some member, this angel, is a cat. So what can we conclude from this? Well, by modus ponens, we can conclude that if angel is a cat, then angel is a mammal. And if angel is a mammal, then angel is warm-blooded. We write it like this. Now, these may seem like trivial examples, but we have to have valid rules of inference. We can't just be saying, oh yeah, we can conclude this. You know, we can just decide whether or not something is true without some valid rules in place. Now, logical proofs such as these are very important in computer science. See, often we write programs or algorithms, we want to know that they will always execute correctly. But how can we do that? We can't test the algorithm or program on every possible input, and so we rely on proofs to make sure that they will always produce the correct input. So let's now look at an example of a logical proof involving rules of inference. So here we have a proof that if we start with these two premises, we conclude this one here. So we've listed here the rules of inference that we've used. We're going to determine whether or not this is a valid proof. So of course we're starting with these two premises. They're arbitrary statements P and Q, so we've got no problem here. Now number 3 uses the rule of inference existential instantiation. So this part of the proof is correct. See, if we have that there exists an x such that qx, we're starting with the point that Q is true for at least one value of X. And we can just call that value of X A. That's what instantiation means. We instantiate X with A. Now, A here is very specific. Because we don't know for sure that Q applies to all of X, we only know it applies to at least one, and we will call that one instance A. So this part is true. Now, if we look at the next line, we've used modus ponens. Now, I mentioned that before. The rule of inference modus ponens basically says that if X implies Y and X is true, then Y is true. That's basically the definition of this operator, the implication. But here, we've done it sort of the opposite way around. We have started with the premise that P implies Q. We've assumed that Q is true. That was the second premise. And then we've concluded P. This is a wrong use of modus ponens. And I'm sure you know by now that P implies Q does not necessarily mean that Q implies P. So this is where the error occurs. And one error is enough to make the whole proof invalid. I'll just mention anyway that going from this step to this step, that is correct. If this was true, then this would be true. If P is true for some value of A, it is definitely true to say that there is some X for which P is true. That's what we mean here by generalization. But the error was going from this step to this step. So even though it was okay to go from 4 to 5, even though this was a valid use of rules of inference, because this was not necessarily true, it doesn't follow from 3, our whole proof is invalid. So this is what logical proofs look like. To construct a valid one, you have to start with a series of premises, and then you deduce things using valid rules of inference. But even though I wrote modus ponens here, we didn't actually use it. Modus ponens says something different than how we used it. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.